morning, my dear students. Welcome back to Structural Analysis 2. Unit 2 we are going to start now. So in this session we will discuss a little bit of lateral load analysis using approximate methods. So JNTUK Structural Analysis 2 syllabus, Unit 1 we have exhaustively discussed about the arches, 3-hinged arches and 2-hinged arches. And let us now see Unit 2 uh, topic, lateral load analysis using approximate methods. Okay, right. When you go into the topics, we have two methods to discuss, which are approximate methods for lateral load analysis. The topic name itself is approximate analysis of building frames. So the two methods namely are portal method and the cantilever method. So if you see the figure that appears to the right of the screen is right. So you have a building frame given, a two-dimensional building frame given, which is having two-story and two bay. Okay, so it's of consisting of foundation as well as this of foundation level and the first floor level and the second floor and the roof level. Okay, so this is a typical two-dimensional building frame given. So if you have some loads acting on this, particularly what we are expected to do in this unit is we talk about only the lateral load analysis. When there is a lateral load acting on the building frame, how you are going to analyze in an approximate manner, not exact analysis. So see the clear difference here. We are not going to analyze this frame for its actual analysis. We are going to have only the approximate analysis, right? So that is how we will see it, right? So let's see something related to this lateral load analysis. So in order to estimate the preliminary size of different members, approximate methods are used. Okay, so why you want the preliminary size of different members? So you might have used your package STAD Pro or else any other software that you might have used. So before you start analyzing and designing a member or the structure, you are required to assign some size. Okay, so maybe you will be assigning, say for example, for a beam 230 mm by 300 mm. Okay, for a column, a 300 by 300 column. Likewise, so you are going to assign some size. It's just from the preliminary knowledge that you have in civil engineering. You don't know whether the size given by you into that software is satisfying or the safe or okay for design purpose. You don't know. You just give a size and run the analysis. Then when it goes to the design process, it modifies the size to suit for all the checks that it has. So this is what you do. So that's the same way you need the preliminary size of members to have an approximate estimate of the uh, bending moments, shear forces, and the axial forces in various members. This is what is required. Okay, so is it clear now? So why we want approximate method to be discussed? Why not exact method? Okay, so when you really want to execute a structure, we need the exact analysis. Okay, so there are two things here. One, to arrive at the exact size of the member, first to analyze the structure, we need to assign some preliminary size, which is approximate size. And the second thing is, when you are not going for exact construction, you are just at the stage of planning, you are going to quote the project. So if you are a project manager, or else working in a project office, right, you are going to estimate a project, then you will quote the project, so you will go for tendering. Then once it is approved for you, then you are going to have a execution. So before all this, how do you quote your price? Is just to estimate approximately, so you don't need exact analysis there. Okay, so in those cases we go for approximate analysis, right? So before applying approximate methods, so when you compare the actual method and approximate method, definitely approximate method should be a little bit easy for you to do it rather than exact analysis. So for that, when you talk about analysis, so determinate analysis is easier, little bit simple than the indeterminate structural analysis. So you take a structure, so you find all the structures practically they are indeterminate structures. So if you want to make your analysis simple, you should make that structure as determinate. So that's the point which is discussed here. So before applying approximate methods, you need to reduce the given structure uh, into a determinate structure by some conditions or assumptions, whatever you call. Okay, because if you have an indeterminate structure, so you have some excess equations required, in a simple manner to say. So if you are thinking of solving an indeterminate structure, what do you have? You have determinate, I mean to say, equilibrium equations plus some additional equations are required. So that is what is here. That additional is, now we are going to meet them by the way of assumptions. Okay, so some equations, equilibrium equations are available, plus to make the structure determinate, so you need some assumptions or equations, additional equations. Okay, right, that's how we are going to uh, uh, convert or reduce the indeterminate structure to determinate. Okay, so here particularly we are expected to analyze a building frame for lateral loads. How you are expecting lateral loads is by the way of wind and earthquake loads, okay, that are going to be acting on the building frame, right? So uh, building frames must be designed to withstand lateral loads. Okay, so you have approximate methods for gravity loads also. So that's out of our discussion here. So your syllabus is meant for uh, discussing lateral loads only. Okay. So if any building frame subjected to lateral loads, so any size of the frame, whatever may be the size of the frame, it may be a now 10 by 10 storied building, whatever may be the size of the building frame, you are able to estimate it in an approximate manner. That is motto of this. Okay, the objective of this topic, the unit 2, is if you have a building of any size, whatever may be the size of the building, you are able to do the approximate analysis, not the exact analysis. Okay, so approximate analysis, by doing approximate analysis, you need to arrive at some moments, shear forces, and axial forces in the members. Okay, so internal forces, the other way, you need to solve for internal forces in a simple manner. Like so, when you are making some assumptions, means you are simplifying the analysis. That's a well-known fact. So whenever there are assumptions involved, means your analysis became much simpler. Okay, so this is how we are able to do it. Let's see some example. So we take a two-story, two-bay multi-story frame subjected to lateral load. Okay, so if you want to analyze this one, just think of analyzing this building frame. So what do you do? First you estimate no static indeterminacy of this. Okay, let us estimate first static indeterminacy of this structure. Okay, so the very simple way of finding the static indeterminacy of building frame is just to make the structure into simple cantilevers. So let us cut the frame here, cut the frame here. So what happens? This portion of the frame is now a cantilever. So it's like this. Here is a fixed support. It's like a cantilever. Okay. So same way, if you cut the frame here, if you cut the frame here, and this one is going to become another cantilever, and automatically this is going to become another cantilever. So there are three cantilevers that you obtain by making the proper cut suitable minimum number of cuts. Okay, so this is another cantilever and another cantilever. Okay, so this is how the frame is being made into determinate structures. All the three that you observe here are determinate structures. So to make an indeterminate structure into a determinate structure, how many minimum number of cuts required in a building frame? This is the way that you find static indeterminacy. This is extensively discussed in our structural analysis. So there are 4 cuts required. 1, 2 here. So this is 1, this is 2, and third one, and fourth one. So 4 cuts required. So each section that you made here will have 3 internal forces. Okay, so the maximum possible reactions are the forces, internal forces are 3, right? Bending moment, shear, and axial. Okay, because this is a 2-dimensional structure, so for a 2-dimensional structure, the maximum possible forces that you can apply is horizontal, vertical, and rotation. Okay, so horizontal reaction, vertical reaction, and rotational reaction, nothing but bending moment. So the total internal forces uh, are 12. So static indeterminacy is 12. Okay, so that's what is mentioned here. The given frame is statically indeterminate to degree 12. So hence you need 12 equations to solve this structure. Okay, got it. So 12 additional. Okay, this is indeterminacy that we are talking about. So this is excess reactions present in the structure. 12 excess reactions are present other than the three equations. Okay, so you need 12 assumptions to reduce the frame into statically determinate structure. Okay, so how many number of additional equations are required? It is equal to indeterminacy. So 12 is the indeterminacy value of the given frame, 2-bed 2-storied building frame. So you need 12 uh, additional equations. So we are talking about additional equations in the sense we are taking them as assumptions. So if you can make 12 assumptions, then your indeterminate structure will become determinate. Then your the solution will become simple. Okay, this is what we plan. Okay, so just see another example how the assumptions are going to be and how the assumptions are going to lead to the methods that we talked about in the previous slide. Okay, right. So the example now taken is of 2-bay single-storied building frame. Let us say 2-storied single 2-bay single-storied. Okay, right. So now if you say a lateral load is acting, let us observe the deformed shape of this. Okay, so this is going to deform like this. This is the deformed shape. Okay, and this is how the beam is going to deform. Okay, so now you observe here. Okay, so this is the middle of the column. So it is going to have the bending outward. Then you see remaining half of the column is going to have bending in the opposite direction, inward bending. Okay, this is outward bending, this is inward bending. So the change point, bending change point, is the middle of the column. So what do you call this? Point of contraflexure or inflection point. Okay, inflection point or the point of contraflexure or point of zero moment. Likewise, you call it different names. So same way for a beam, if you see, so half of the beam is going to bend like this, sagging. Half of the beam is going to bend like this, hugging. So if you have a frame, if you push the frame from one side laterally, this is how you observe the bending nature. So same way, each and every column will have the same behavior and each and every beam will have the same behavior. Same here, you will have an inflection point that is shown with a small circle at the middle of the column. Okay, so this is how, like this. Okay, so what does this mean? So you have inflection points at the middle of the members. Okay, when you have a lateral load acting on the building frame, you have an inflection point or bending moment 0 point in the middle of the member. So number of members in a structure will have, you know, those many number of zero moment points. So those are your equations. Zero moment is zero. You have just seen in case of three hinged arches. So the crown point is having a hinge. So there you are having the third equation, bending moment at crown is equal to 0. So same way here also you have inflection points at the middle of the members. So number of members is equal to the number of additional equations available. So you have say for example the previous example, the two-story two bay. Okay, so members here, number of members here are 1 2 3 1 2 3. So total 6 columns available, and then 1 2 3 4 beams available. So total number of members are 10. Okay, so there are 10 equations available. With what assumption? The assumption here is each and every member has a point of zero inflection at the middle. Okay, so this is the assumption that we are making. So that single assumption is giving you, now, a 12 degree of indeterminacy. So which means you need 12 equations. So with just one assumption you are getting 10 assumptions, 10 additional equations. So there are two more left. So if you can make two more equations, then your structure is very simple to solve. Okay, so total unknowns in the structure are 15. Right, so 3 equilibrium equations available, 12 excess. So those 12 you need to get it by some assumptions or conditions, whatever it is. So by the assumption, one assumption that each member has point of contraflexure at the middle will give you 10 assumptions. I am talking about the example that two-story two-bay frame. So there are still two more equations required. So that depends on the method, portal or cantilever. How you are going to get those two assumptions is explained in this two methods. So there is a difference between getting those two equations by the two methods. Okay, so this is clearly how we are planning for approximate analysis of a frame, building frame. Okay, right, so it's just throwback the topic. So lateral load analysis of building frames by approximate methods, this is your topic. So why you need approximate methods? There are many situations where you need only just the idea about the analysis of the frame. So where you don't need exact size of the member, exact steel in the structure, just a rough estimate is required. So I told you the two situations. One, for example, if you are going for solving the structure using a package, you need to first assume a preliminary size of the member, then you have to proceed for the analysis, that is approximate analysis. Right, once you design the structure, then you get the exact size of the member. Then by giving the exact size of the member, then you run the analysis, that is the exact analysis. Okay, so such is the situation. The other case, when you are when you deal a project, um, if it is in the stage of just quotation stage. So when you want to quote the price for a structure, you just need approximate size of the member, approximate steel quantity. So then based on that you quote your price. Once the project is approved, then you are going for exact analysis and design so that the execution happens. So for the from the approximate analysis, the design that you are getting, you are not going to execute it, remember. So it's just for an idea upon a project. Okay, right. So we have two methods for approximate analysis of lateral loads. There are approximate methods for gravity loads also, but your topic is only to talk about lateral loads. So portal method and cantilever method. Okay, so half of your unit 2 will be portal method and other half of your unit will be cantilever method. Okay, so the based on the assumptions or the conditions that you assume in these two different methods, you are going to make the structure determinate. uh, the indeterminate structure is reduced to determinate to make your analysis simple. You will see when you uh, actually proceed for the analysis how simple it is. Okay, right. Thank you.